So when we're trying to optimize, we're really trying to find what is the best value for a given situation. So we're going to try to model different situations with functions and then use the ability that we have to find maximums and minimums using the derivative to optimize and find those maximums and minimums that are going to help us give the optimal values that we need. So the first thing is we have a couple of guidelines that we can use when we're doing optimization. First, we need to read the problem carefully. We're going to identify what the variables are, organize the information, maybe make a picture, and then with that, we're going to identify what is our objective function, which is the function that we need to optimize. Then we're going to write it in the terms of the variable of the problem. Sometimes we have one or more variables, but we need to make sure then we identify constraints, so things that are going to limit our problems, and then later with the constraints, use the constraint to eliminate all but one independent variable in the objective function. Then after that, being that a one variable function, then we're going to express the function in terms of that single variable in a given interval that we are interested in. We're going to use methods of calculus to find the absolute maximum or the absolute minimum of the objective function. If necessary, we're going to check endpoints in case the interval is close, or we check for critical points. Now, let me give you an example of that going on. So the following table is going to display a few cases on how the product of two non-negative numbers varies while their sum remain constant. The condition is that the sum of these numbers is 20. Notice that there's a lot of numbers that can give me sum 20. It can be 10 and 10, or 19 and 1, or 15 and 5, so on. Okay, this is going to be my constraint. Now, we want to maximize or minimize what the product is. So first, we're going to write a couple of numbers. Notice we have x and y. Then we have the sum of those, and we have finally the product. So with this, we have 1 and 19, 5.5 and 14.5, 9 and 11, 13 and 7, 18 and 2. But since these are real numbers, there are an infinite amount of number so that the sum is 20. Okay? But we are interested not only in that the sum is 20, but that the product is maybe the maximum possible. So, of course, what we can do is we can replace one of these variables. Notice that we can say y is 20 minus x and replace in the product. So my product is going to be now x 20 minus x, right? This is x times y, and x times 20 minus x becomes 20x minus x squared. That's a quadratic function. That's giving me a parabola that is opening down. And notice that this is going to have a maximum point that we can find via the parabola, or we can find optimizing. This is going to be the maximum when x and y are 10. The product is going to give me 100. Okay, so this is my objective functions. And given that we have 20 minus x, we're going to have a very well-defined boundary in the numbers. I can only go really with this boundary from 0 to 20 in the y direction and 0 to 20 in the x direction. Because remember, the sum needs to be 20. So the worst case scenario is when x is 0, y is 20, or when y is 0, x is 20. And so all those infinite numbers that are here is everything that is possible for obtaining 20. Now, another classic optimization problem is about constructing a corral for fencing. So a rancher has 400 feet of fence for constructing a rectangular corral. One side of the corral will be formed by a barn that requires no fence. 3 exterior fences and 2 interior fences partition the corral in 3 rectangular regions. And so this is going to look like this. Notice I have the barn over here and the corral is over here. And we have 2 partitions over here splitting the corral in 3. Now, I don't know what are the dimensions of this, but I'm going to call this side X, and I'm going to call this Y. Now, this is going to give me 4X plus 1Y, and that needs to be the total fence that I have. So this is going to give me my constraint. Notice 4X plus Y needs to be equals to 400 feet of fence. So this is my constraint function. This is the first thing that I get. Notice that you can identify the constraint because it's always a function equal a constant number. Okay? Now, we want to find the dimension that maximizes the area enclosed. So we want to maximize X times Y. And so we're going to do pretty much the same that we did before. And we can find the objective function. Notice Y is 400 minus X. Times X is going to give me 400X minus 4X squared. And so similar to before, we have a quadratic function that is going to give me a parabola that has a maximum that I can identify easily with the vertex, or I can use the derivative to find that. So different approaches. Of course, at this point, it's very easy to find the critical point with the derivative. Notice A prime is going to be 400 minus AX squared. So then again, making that equal 0. And let me get the board so I can show you. So that'll be A of X, 400X minus 4X squared. The derivative A prime is 400 minus AX. So now critical points is when A prime is equal 0, which is equivalent to 400 minus AX equals 0. That implies that 400 is equals AX, or that 400 divided by X by 8 is X, and that's going to give me 50. Okay? Notice that you can also get that information from, in this particular case, from the fact that this is a parabola function, right? So you identify this like a parabola. This is A, this is B. We don't have C, but we don't need that. The vertex is given by on the X coordinate, and the X coordinate is given by minus B over 2A. And F of that's the vertex. And so notice that this is going to be pretty much minus B, which is minus 400, over to 8, which is minus 8 from here. And so that's going to give me 50. And so we're going to have 50, F of 50. And that's where the maximum is going to be located, the vertex is going to be located, and so we have that maximum. So we have the optimal solution here is going to be given by 50, 10,000. Now let's go for another example of this. We'd like to make a box with a square base. Notice a square, that's the same dimension. And suppose the sum of the base length in width is 64. So we want to find the dimensions of the box that give the largest volume to the box. So always important to make a picture. Notice we have a square box with base from side W and YW, and we have height H. Okay, so the objective function, of course, is going to be the volume, and the volume is going to be given by W squared, which is the area of the base, by the height. So W squared times H. Now we do have a constraint that the sum of the base length and y needs to be 64. So that means 2w and h needs to be 64. Now, using that, we can very easily change h by 64 minus 2w. And we're going to get this objective function here, b equals 64w squared minus 2w cubed. Let me again show you how did you get to that point. So we're coming from these two things. We have volume is w squared times h, and we have 2w plus h equals 64. So we replace h by 64 minus 2w, switching sides. And now I'm going to find volume, which is w, and we're going to change h by 64 minus 2w. So that's going to give me 64w squared minus 2w cubed. And that's a function now that is going to be just in terms of w. As you can see, we change from having a function that has two variables to just a function that has one. Now, given that, we can find the derivative. B prime is going to be 128w minus 6w squared. Now at this point, again, critical points. The critical point likely here is only when b prime is equal to 0, and that means that 128 minus 6w times w should be equal to 0. That's going to give me two cases, w equals 0 or 128 minus 6w equals 0. I'm not going to follow the direction of w equals 0 because that means that we don't have a box at all. So it doesn't make sense. So now we're just going to follow this direction, and we get 128 divided by 6 is going to be w. If I take a second derivative, notice that the second derivative of this is going to be 128 minus 12w. Which, if we check what the critical point is, notice that the critical point is at 64 over 3, which is exactly the same as 128 over 6. Then at that point, we're going to have a maximum. Okay, it's going to be an optimal solution. Our second derivative is going to be negative. (64/3). You can now plug second derivative of 64/3, and you're going to realize that this is much more larger than 128, and so this is going to be negative, and this critical point is going to be a maximum.